In this section, we're looking at line integrals of vector fields. One of the most important physical applications of line integrals is that of finding the work done on an object moving in a force field. For example, this figure shows an inverse square force field similar to the gravitational field of the sun. And the closer you get to the sun, which would be right here in the origin, the stronger the gravitational field. So the length of those vectors as you get closer is going to be longer. The further away, you've got the shorter vectors. And suppose we're moving through this vector field along this parabolic path. We want to calculate the work done in moving along this path within this vector field. To see how a line integral can be used to find work done in a force field, consider an object moving along a path C in the field as shown. So again, we're moving along this path, but there's a field, an infinite field of vectors. At each point on C, the force in the direction of motion is equal to the dot product with their F and T, where F is your vector field, T is your unit tangent vector, times that unit tangent vector. Now the definition of a line integral of a vector field is as follows. F is a continuous vector field defined on a smooth curve C given by R of t, where the time intervals from A to B. The line integral on F of F on C is given by this line integral of C of F dot dr. Again, F and R are in bold, so those are going to represent vector functions. So this is equal to the dot product of your F with T ds. And then further, this can be written as a single definite integral from A to B, where A to B is the time interval on the path, and you're going to replace every x in the vector field F with what it equals on the path. You're going to replace every y and z in the field with what it equals on the path, and you're going to find the dot product of that with your r prime of t dt. And again, your r prime of t comes from your r of t, which is your path. So the line integral for work in a vector field, it's a line integral on the path c of f dot dr. Here's an example to find the work done by a force field. The force field is capital F, that bold F of xyz is equal to negative 1/2 xi minus 1/2 yj plus 1/4 k on a particle as it moves along the helix given by r of t equals cosine ti plus sine tj plus tk. So the path is your r of t. The field, it's an infinite field of vectors. Now we've shown just a few of the vectors that are on that path. From the point 1, 0, 0, all the way around to this point over here, negative 1, 0, 3 pi. Now these are points on the path. Now you do need to determine the time interval where you will start at the point 1, 0, 0 and end at the point negative 1, 0, 3 pi over 2. One way to define that path is to look at the components here and look at the simplest component. In this case, is z on the path is equal to t. That's the parametrization, z is equal to t. So if your z starts out at 0, then your t is also going to start out at 0. If your z ends up at 3 pi, then your t is also going to end up at 3 pi. So in this case, the time interval is going to be from 0 to 3 pi, although it's not given yet here. That's how you would determine the bounds of the definite integral. Now, because r of t is your components, again, you can say that x is equal to cosine t, y is equal to sine t, and z is equal to t. That's taking the path that they've already given you and setting the x, y, and z equal to what the components are. You can then rewrite that vector field by replacing the x, y and z in the vector field with what it equals on the path. And when you do that, you get this vector field in terms of t, where when you started off, the vector field was in terms of x, y, and z. So to find the work done by that force field in moving a particle along the curve C, we want to use the fact that you're finding r prime of t. You have to take that F vector field in terms of t and multiply that by the dot product of the r prime of t dt. You take the derivative of your path to get negative sine ti plus cosine tj plus 1k and write the following. The line integral for work is found by setting up a definite integral from a to b of that vector field, replacing all the x, y, and z with what it equals on the path, and then finding the dot product of that with your r prime of t and then dt. So by replacing all the x, y's, and z's of the vector field f with what it equals on the path, you end up with this vector here, and you find the dot product of that with the derivative, the r prime of t vector. Find the dot product by multiplying the corresponding components and adding the results. You end up with this single definite integral. Notice the dot product is a scalar, so you are not going to be having any vectors in this step here after you find the dot product. You can then simplify it because these end up being opposites, and we get this pretty simple definite integral from 0 to 3 pi of 1/4 dt. And then when you evaluate that, we get 3 pi over 4. So this is going to be the work done on that object as it's moving along that helix within that vector field. Okay, in this example, I'd like you to try this one on your own. Evaluate the line integral for work. Find the work done by the force field, where your force vector field is f of xy equals 3xi plus 4yj in moving a particle along the curve where r of t equals ti plus the square root of 4 minus t squared j for the time interval from -2 to 2. You can try this one on your own and then come back and check your solution. Okay, let's begin this by looking at the path itself. We can use a graphing calculator to make a quick sketch of the path. The path is r of t equals ti plus the square root of 4 minus t squared j along the time interval from -2 to 2. Now, I've already made sure my calculator's in parametric mode, and when you go to y equals, you can enter what the x equals t and the y equals square root of 4 minus t squared. And then I've adjusted the window so that the time interval goes from -2 to 2 with a t-step of 0.1. And then I've also adjusted the bounds there. When you graph that, you see the path here. The object is moving along this path starting at t equals -2 within the vector field. The vector field itself you're not going to graph, but you can imagine an infinite field of vectors here, and the object is moving within that field of vectors, and we want to calculate the work done. So to do this, we need to replace the x and y in the vector field itself with what it equals on the path. And then we also want to find r prime of t, and then we're going to do the dot product of those. So let's go ahead and find r prime of t. R prime of t is found by taking the derivative of this. The derivative of t is 1, so it's going to be 1i. Now the derivative of the square root of 4 minus t squared, you're going to need to use the chain rule. This is the entire quantity to the 1/2 power. So that derivative is going to be 1/2 of the quantity 4 minus t squared. And subtract 1 from the power, you get -1/2. Multiply by the derivative of what's inside to get -2. And now that's -2t, sorry. That's times j. When we simplify this, we get 1i plus that 2, the -2 and the 1/2 will simplify, and this -1/2 power, we can write it as a fraction. So we simplify this to have a -t in the numerator and the square root of 4 minus t squared in the denominator. That is going to be your r prime of t. now we want to replace the f in terms of x and y. We're going to replace the x and the y with what it equals on the path. So this work is going to be a definite integral from a to b of this f, but you're going to replace the x with what it equals on the path in terms of t, and the y with what it equals on the path in terms of t. Dot that with r prime of t dt. Okay, are you ready for this? So our definite integral becomes the integral from a to b. Our time interval is given to us from -2 to 2. And our vector field f is 3xi plus 4yj, but I'm going to replace the x and the y with what it equals on the path. So this is going to be the path, the vector 3 times x, but x is t. So that's 3ti plus 4 times your y, but y is equal to, again, you can look at the path and you're going to make the substitutions. X equals t and y equals the square root of 4 minus t squared. And that's what I'm plugging into this vector field. So that's going to be 3ti plus 4 square root of 4 minus t squared j. Okay, so that's your f vector, and you're going to dot that with your r prime of t vector, which I've calculated here, is 1i minus t over the square root of 4 minus t squared j, and all of that times dt. Let's simplify this. When you find the dot product, you multiply the corresponding components. Let's multiply 3t times 1, and that gives us 3t. And then let's multiply 4 times the square root of 4 minus t squared with this negative t over the square root of 4 minus t squared. Well, those 4 minus t squares are going to cancel out, so it's going to be this times 4 times a negative t, and that is going to give us a negative 4t, all of that dt. So now we end up with this single definite integral from -2 to 2 of negative t dt. When you evaluate this, you will find that this line integral for work ends up with a value of 0. Now you may think to yourself, how can work equal 0? Well, in physics applications, when you're finding work, there are some cases where the work is positive, and there are cases when the work is negative. So perhaps on part of this path the work is positive and the other part the work is negative, so they end up canceling each other out. So in this case the work is equal to 0.